See this little guy here? That's my pointer. Okay, so you gotta use your imagination a bit. But don't worry about it. It's pretty innocent looking for such a little box. But it turns out, there's a surprising amount of complexity in there. Pretty much all of which I had the joys of discovering when adding cursors to our Wayland compositor. Let's talk about it. We've all used computer mice before. You point, and you click. How hard could that really be, right? So those two things, turns out, not hard at all. It's pretty easy, actually. But when you consider things like the different hardware capabilities and the different, preferences of your users, some of the real complexities start to come into play. So things like trackpads versus scroll wheels, kinetic scrolling, actually getting the cursor image displayed on the screen is surprisingly tricky. So there's a whole bunch of things that start to really add up. Are we going to have all of that implemented and functional by the end of today's video? Probably not. But I got everything implemented that I could using the test hardware that I have lying around, which is this here computer and this here mouse. And yeah, trackballs are obviously the best kind of mouse. So with that cleared up, on to the next topic. So there are two pieces to this: putting an image into a buffer, and then putting that buffer onto the screen. If we look at the first piece, your Linux OS probably has a bunch of cursor images somewhere on your file system. Wayland provides an easy way for clients to load these images, but compositors are left a little bit more on their own. There's another library that should help here called libxcursor, which takes care of loading the images into a buffer for us. To keep my compositor's code a little bit more simplistic for now, I'm just going to create a buffer and then fill it with red. This is obviously going to change eventually, but I figure the bright red box is going to be a lot easier for you all to spot and follow on the screen anyway, so, win-win. Okay, so now that we have the cursor image in a buffer, let's talk about actually getting it onto the screen. To do this, there's the good way, and then there's the bad way. But here's the catch. The good way doesn't always work, and it has a lot more headaches that you've got to work through. But first, story time. Way back in Devlog 2, we set up our rendering pipeline, which is the thing that lets us draw onto the screen. The very short version of it is that we create a buffer using something called GBM. We populate it with OpenGL, and then we send it out to the monitor using the Linux DRM subsystem. The DRM piece has this concept known as planes. Not that kind. These planes are basically just rendering layers that stack on top of each other to make a complete image. Your physical hardware and your Linux kernel version are what determine how many of these planes you have, but modern hardware should have at least the primary plane, which is just a single plane that you render everything into. Some systems come with what's called a cursor plane, which is a much smaller plane, and it's specifically intended to render mouse cursors. And this is good because you can move the mouse cursor around without needing to re-render anything that's in your primary plane. If you use a cursor plane, though, there's some hardware constraints that you got to take into consideration. For example, on some systems, the cursor plane is very tiny, and clients are what determine what the mouse cursor looks like. So if they give you an image that is far too big for your operating system's cursor plane, guess what? You got problems. The biggest challenge, though, and this is the one that ended up tripping me up, is that cursor plane, it might not even exist. And if it doesn't exist, well, you can't really use it. So, regardless of whether your hardware supports a cursor plane or not, you're going to need to implement some kind of fallback, which is pretty much always to just render the cursor alongside everything else in the primary plane. You just want to be careful to draw the cursor on top by drawing it last. Since my setup apparently doesn't even have a cursor plane, This was my only approach, so it's what I went with for now. And there we have it, our beautiful cursor on the screen. Sure would be great if we could move it around though. Moving the cursor inside the compositor is pretty straightforward. We've already used libinput in past videos to handle other input events like keyboard key presses and device hot plugs. Turns out they also offer a pointer motion event, and this fires whenever the pointer moves. All we need to do is pull the change in X and Y values out of the event and then add it to our cursor's position. And would you look at that? Works like a charm. Oh, right. So we also got to keep it within our monitor's bounds. There we go. Much better. Now, let me ask you something. If I were to move this cursor over an application, what do you think should happen? Who owns the cursor? Is it the compositor or the client? Ultimately, the compositor gets final say in everything, but the client has a lot more influence on the cursor than I'd originally thought. When the cursor enters the bounds of a surface, the compositor sends that client an enter event. And similarly, when the cursor leaves the bounds, the compositor sends a leave event. When the client receives the enter event, it should almost definitely respond to it with a set cursor request, which contains a Wayland surface that specifies the cursor image that it wants to use. It's then the compositor's job to display the correct image instead of the one that it's been using. I have the test client creating a new surface on startup for the cursor, and then filling that buffer with the test client's background color. On the compositor side, our render method, specifically our render method for the cursor, first checks to see if the pointer is above a surface, and if so, then we use whatever surface that client gave us for the cursor. If we take a quick look, our cursor is now a different color when it enters a client. There is one more compositor side capability that I added for pointers, but this was just meant to be temporary code in order to make testing a little bit easier. Basically, if the cursor is above a surface and the user has the super key held down on their keyboard, then moving the mouse is also going to move that application window. So far, nearly everything has been handled compositor side, but in order to wrap up the pointer capabilities, we're going to have to send a whole bunch of events over to the clients and have the clients handle those in some way. The first few are easy. For both pointer motion and button presses, we just take the event that libinput gives us and pull a bunch of data out of it, and then repackage that data into a Wayland event that we send. It's just worth noting that you only want to send this to whatever surface the cursor is currently above. Then over in the client code, we'll handle the motion events by just updating the circle's position. So essentially the circle is going to follow the mouse cursor around. And then for the button event, we're going to randomize either the foreground or the background color, depending on if the user clicked the left or the right mouse button. Remember, these behaviors don't actually have to be useful. They just need to show that the communication is happening correctly. And if we test this out, all right, it looks like it's working. It's also worth noting that if we have two clients open, only the one that has the mouse cursor, the mouse focus, is the one that's changing. All right, now for the last event, or should I say 6 events. Scrolling. See this thing here? I move wheel up, screen goes down. I move wheel down, screen goes up. Why does it need to be any more complicated than that, you ask? Well, see this other thing here? this is a trackpad. It also does scrolling. Only here's the thing, if I flick it, it keeps scrolling. And if I flick it and then put a finger down, it stops immediately. And check this out. I've got my Figma dock here. Using 2 fingers, I can just scroll around in any direction I want. Amazing, right? All of these behaviors need to be captured in some way inside of the Wayland protocol. And that's where all the complexity comes from. So if we go back to the mouse wheel and I start to scroll, you might notice that it has notches that it stops at. So click, 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 click. Did you know that these notches are actually somewhat standardized and that high precision mice exist which have different numbers of notches, or for that matter, even no notches at all? If you're scrolling up and down a long web page, it's not too important. But if you're moving your selection up and down in, say, a specialized drop-down menu, you'll need 1 notch to correspond to 1 item in the list. Also, some mouse wheels actually let you click to the left and right to scroll horizontally. My mouse doesn't have that, so until I get a new mouse, probably not going to be adding that capability to Breezy. But anyways, all of that stuff is what makes the Wayland protocol so complex for scrolling. Turns out there's a lot to it. All of these axis events are what's used for the different approaches to scrolling. In my current setup, I don't have a trackpad attached to the computer that's running Breezy, so I've really only implemented and tested the very basic scroll wheel events, which in this case is axis and axis value 120. To go along with those, I'm also emitting events for axis source and frame, though my test client isn't really making use of them at this point. These are all implemented pretty much the same way as our other libinput events. So the libinput event fires, and we've got a special handler for that particular event type. And inside of that handler, first we check to make sure that the pointer is above a surface, and if so, then we fire the appropriate Wayland events to that client. Over on the client side, I was struggling to come up with something that was both quick and easy to test these events with, so I ended up just changing the size of the circle. As you scroll in or out, the circle either grows or shrinks. This probably wouldn't be sufficient for anything that's, more advanced than the very basic scroll wheel events, but since that's all I've implemented so far, we're good. And if we do one last test of all of our beautiful new features, we have, your basic cursor moving. We have window activation. We can move the circle around. We can change our colors. We can grow and shrink the circle, and we can move around the active window. Everything works wonderfully. I think we're actually starting to near the end of phase 1 for the project, so that's exciting. We've got the display output pipeline all in place. We've got the Wayland communication piece in place, and we've got a lot of that core Wayland protocol actually implemented and functional at this point. There's still an endless list of hopefully non-essential protocols to add, but I'm planning to just implement those as they come up. I'm guessing we're probably going to have about 3-ish more videos to do to wrap up phase 1. So in the next video, I'm going to be working real hard to try to get a functional third-party client working inside of our compositor. I think that's really going to make the compositor, feel more alive, feel like it's actually working. And then after that, I've got just a giant list of desktop features that I want to get added in. So things like window tiling and an application launcher. So I'm guessing all of those things are probably going to take, roughly 2 more videos, but, we'll see. We learn as we go, right? But anyways, I think that's about it. So thanks for watching, and I'll catch you in the next one.